So in the last session, we've been talking about the necessary and sufficient condition for a field to be a splitting field. So let us try to prove that the theorem. The theorem is like this. If E is a field such that F is a subfield of E, which is a field of F closure, where F is another field, then E is a splitting field if and only if every automorphism on F closure induces an automorphism on E. There are two parts here to prove. One is E is a splitting field implies every automorphism on F closure induces an automorphism on E. And the second part is if every automorphism on F closure induces an automorphism on E, then E is a splitting field. So let's prove the first part. So E is a splitting field. And that implies there exists a collection, let us say K is equal to Fi of collection of polynomials in f of x for some I from some index set I such that every zero of elements in K, elements in K is they are polynomials in K, so there are zeros of every zero of elements in K are in E. So let us assume that A is equal to alpha j, j belongs to some index set j, B the collection of all zeros of every element in K. So now what we do is, let S be a set of all finite sums of finite products of elements from A union the multiplicative identity of F closure. You want to add this one also, otherwise you are skipping the F. This is our F closure, F, and there is an E here. E contains all these alpha 1, alpha 2 dash dash alpha j. And these alpha j's are all zeros of a collection of polynomials of fi of x. And these fi is x are, these polynomials are in f of x. And this set is our A. I'm going to add the multiplicative identity of F closure also. That, see, the idea is to prove that E is generated by this set. If you don't have 1, that it won't contain F. It will contain only the outside of F. That's why I used 1 here. So we are assuming that S is a set of all finite sums of finite products of elements, which means that an element of S would be like this: A0 plus A1 alpha 1 plus A2 alpha 1 alpha 2 plus A3 alpha 1 square alpha 2 alpha cube alpha 3 cube. Any combination of finite products of elements from here and the sum. See, one thing we need to note here is these alpha j's are all zeros of polynomials from K. So all these have some degrees, a finite degrees. For example, degree of alpha j over F will be some nj. So in this combination, for nj, it won't go beyond nj minus 1 power. Just want to let you know that these powers will not go indefinitely. Okay? So these are the types of elements you can see it in S. This implies, actually, I'm not going to give you the proof of this, it is simple. This implies S is a field to be verified. What are the things you need to prove here? You need to prove that S is a group under addition, which is definitely true. 0 and 1s are elements of S. Then for every element in S have a multiplicative inverse. So I'm going to leave it to you as an exercise. And this S contains all alpha j's. J belongs to. That is because it's a finite sum of finite products because all alpha j's. And S is a subfield of E. Because all these elements are from E and you are taking the finite sums of finite products, so it has to be an extension of S. But E is a splitting field of this. The definition of splitting field is that it's the smallest field containing all zeros of a collection of polynomials. So since E is the splitting field of K, S is equal to E, because you cannot have a smaller field containing all the zeros of this collection of polynomials. And that implies E is generated by A union 1. That is the idea of creating this S and showing that it's a field. Now, what we want to show is every automorphism on F closure induces an automorphism in E. So we'll take an automorphism from F closure. So let sigma be an automorphism on F closure. So that means, that implies sigma is determined by the elements from A. I'm not going to take 1 because that is trivial, because whenever you say sigma is an automorphism on F, we are assuming that sigma is leaving F fixed. So I'm going to take just A. So determined by the elements from A. Meaning, if you take any elements from E, the value of or the image of that element under sigma is determined by the elements from A. Okay. Now each every conjugate of elements from A is in A. See, this A contains all the zeros of polynomials from K. That means every conjugate of every element in A is in A itself. Meaning A is equal to alpha j in some index at j. So let us take alpha 3. Alpha 3 will be a conjugate of for some alpha 7. And the alpha 3 and alpha 7, it cannot go beyond, the conjugate of alpha 3 cannot be outside A. That's what I'm trying to say. It's actually inside A itself. And the automorphism is determined by elements from A when it is or the sigma is determined by the elements from A. Sigma is determined by the elements from A within E. Meaning, if you take an element from E, the image of that element under the map is determined by the images of alpha j's under sigma. So, and here we will say we have another fact here. Every element or every conjugate of every element in A is in A. And also sigma should map an element in E to its conjugate. What I'm saying is, F closure, this is our sigma. When it comes here, if you take any element, a general element alpha, sigma of alpha is equal to some sigmas of elements from here. So probably sigma of A0 plus sigma of A1, alpha 1, alpha 2 square, etc. Finite sum. That is what I am saying, determined by the elements from A. Then these elements alpha 1 and alpha 2 square, they have to map to its conjugate. So sigma of alpha 1 should be mapped to sigma of, so mapped to the conjugate of alpha 1. So each of these will be mapping to its conjugate, and all these conjugates are still in E. So this portion will be under E. Whatever you are mapping from here should go inside E. So that means sigma maps every element in E to an element in E. But that does not mean that it is an automorphism, because we still have to prove that it is an onto isomorphism. It maps every element E into itself, that's all it says. So we still have to prove that it is an onto. So what we will do is, since sigma is an automorphism, so is sigma inverse. So let B belongs to E. We want to prove that there is an element in E that is mapped by sigma. So that implies B is equal to sigma of sigma inverse of beta. So that means there is an element here that is mapped by sigma to B. That implies sigma is onto. That implies sigma induces an automorphism in Now we need to prove the second part. So what we assume that, suppose every automorphism on F closure induces an automorphism on E. Now we need to prove that E is a splitting field. So what we do is, let g of x is equal to an irreducible polynomial in f of x such that g of alpha is equal to 0 for some alpha in E. We need to prove that this contains all the zeros of a collection of polynomials in f of x. So what we do is, let beta be a 0 of g of x. This beta could be the same as alpha, or it could be any of the 0 of g of x. And that implies there exists a conjugate isomorphism psi of alpha beta from f of alpha to f of beta. So what is happening here is, F closure, same F closure, and there is a E here, there's F here, and we took an alpha from here whose irreducible polynomial is g of x, and beta be another or the same 0 of g of x. Then we are mapping B. We don't know where this B is. It is outside F, but probably not inside E. We need to prove that this is inside E. If this is inside E, then E is a splitting field. But we can always define a conjugate isomorphism from alpha beta, from f of alpha to f of beta. So we can, F closure is a, F closure is algebraic over alpha, f of alpha, because F closure is an algebraically closed set, so closed field, so it automatically is algebraic over f of alpha, and that implies you can extend this to f of alpha. You can extend this conjugate isomorphism to an isomorphism to F closure. So there exists an extension of psi of alpha beta from F closure to a subfield of F closure. So let tau from F closure to tau of F closure be the extension of psi of alpha beta. So this actually from here to is probably a subfield of this is tau of F. Now consider the inverse. Then inverse is from tau of F closure to F. This is actually onto. Tau is from here to here. And we already seen the situation several times. That implies there exists an extension of tau inverse, to F closure to an isomorphism from F closure. But tau is already onto, and that implies tau F closure is equal to F closure. That implies tau is an automorphism. We are creating an automorphism because we are given that every automorphism induces an automorphism on E. So from the existing isomorphism, we created an automorphism. Now we know that this automorphism induces an automorphism on E. Tau then induces an automorphism on E. That implies tau of alpha belongs to E for all alpha in E. And what does this mean? Tau alpha is the conjugate of alpha. That implies tau alpha is equal to beta, and that belongs to E. And that implies E is a splitting field. Because splitting field means we want to write some more steps if you want. See this, we took only one of the irreducible polynomial. We can have several of them. So finally it's going to be E is a splitting field of all the collection of such irreducible polynomial in f of x whose at least one zero is E. So we can write that one also. So E is a splitting field of all irreducible polynomials in f of x whose at least one zero belongs to E. So that is the second part of the proof. So I have a couple of definitions. Let E be an extension of F and f of x belongs to f of x. Then f of x splits E if f of x can be factorized into linear polynomials in E of x. So an example, let f is equal to q, E is equal to q of root 2, and of course f closure is q closure, and f of x is equal to x square minus 2. This x square minus 2 can be written as x minus root 2 times x plus root 2. So x minus root 2 and x plus root 2 belongs to q of root 2 of x. These two are not polynomials in q of x, but still it is a polynomial in here. And x minus root 2 and x plus root 2 are linear polynomials. And that implies x square minus 2 splits q of root. Another example where you don't split the extension, let f is equal to q, E is equal to q of cube root of 2. Of course, f closure is q closure, and f of x equal to x cube minus 2. This actually you can factorize x minus alpha 1, x minus alpha 2, x minus alpha 3. This is actually the real root, that is cube root of 2. This will be, these two are complex roots, complex zeros of x cube minus 2. So, and x minus alpha 2 and x minus alpha 3 are not in q of cube root of 2 of x. If you can factorize into linear, non-linear polynomials here, x minus 1 into a quadratic polynomial, but our definition wants this to be linear polynomial. That means x cube minus 2 does not split q of cube root of 2 of cube root of x. Another couple of different flavors of this definition. F of x splits E if E is a splitting field of f of x. If E is a splitting field of f of x, E is the smallest field that contains all the zeros of this. So f of x can be factorized into linear polynomials in E of x. So f of x splits E. That is one flavor of this. Another one is f of x splits E if every 0 of f of x is in if every 0 is in E, then f of x can be factorized into linear polynomials in E of x.